Thanks for the invitation. So today I'm going to tell you guys about cylindrical contact homology and why it's not such a well-defined homology theory, and in some cases when it can be a well-defined homology. So the first thing I want to do is tell you what contact homology is supposed to be if there were no problems and we lived in a magical, happy world. And then I'm going to break the dream by telling you about the nightmare of multiply covered curves. And then I'll briefly explain how you get around these problems in dimension 3. And then if there's time, I have some nice computations for prequantization spaces that will let you realize the contact homology of prequantization spaces like the sphere. Okay, so the first thing that I should do is tell you what's going on. Okay, so let me just briefly recall what a contact manifold is. So MC is a contact manifold when C is a maximally non-integrable hyperplane distribution and then we're going to assume that C is co-oriented, so this means i.e. C is equal to the kernel of alpha, where alpha is some one form such that either d alpha to the n minus 1 wedge alpha is a volume form, or equivalently that if we do d alpha restricted to C, it's non-degenerate. Okay, so probably everyone's familiar with this, but it's kind of different in symplectic when you talk about symplectic geometry, because with a symplectic manifold, you automatically come with a symplectic form that you want to think about. But with contact manifolds, the interesting structure is this maximally non-integrable hyperplane distribution, and there's a way that you can define there's something called a contact form, which allows you to define the contact distribution as its kernel, but there's going to be lots of different choices of contact forms that give rise to the same contact structure. And so if this condition is satisfied, then you say that alpha is a contact form.
Joanna, is the contact form necessarily globally defined or just locally?
Oh, just so here I said that C is co-oriented, and so if you assume that the contact structure is co-oriented, then it's globally defined as the kernel of a one form. Otherwise, it's local, and then that becomes like a real mess when you want to define the Reeb vector field. So most of the time, people just assume that the contact structure is co-oriented to get around that. All right, and then to every contact form, we can associate a unique Reeb vector field, a unique vector field, which is called the Reeb vector field. Okay, and the Reeb vector field is defined by you want alpha of R to be equal to 1, and you want d alpha of R to be equal to 0. So this alpha of R equals 1, you can think of as some sort of a normalization. And then d alpha of R being equal to 0 means that the flow of R preserves the contact distribution C. Or you can say that the flow of R is transverse to C. And also this tells you that the tangent space of M can be written as the contact distribution plus the Reeb component. Okay. And then sort of a famous conjecture in contact geometry is the Weinstein Conjecture. And this says that let C be a contact distribution, a context structure on M. Then for any contact form, defining C the Reeb vector field associated to alpha admits at least one closed periodic orbit. Okay. So this kind of says something interesting about contact manifolds, because it says no matter what contact form that we pick, there's always going to be one closed periodic orbit associated to the Reeb vector field. So this is supposed to be some sort of like topological qualitative fact about contact manifolds. And then there were a lot of results by Hofer and Zander and Viterbo in like the 80s and the 90s. And then Taubes proved this in dimension 3 using basically Seiberg-Witten theory. And this was like in 2007. Okay. So sort of, if you're familiar with what symplectic topologists do, whenever they want to prove these sorts of qualitative facts about vector fields associated to either symplectic or contact manifolds, they try to do Morse theory, where the critical points are going to be closed periodic orbits, and then the differential, which would count gradient flow lines, is going to count something analogous, which is called a pseudo-holomorphic curve that's going to interpolate between these closed Reeb orbits. And then if you can show that you get a homology this way, or you get a chain complex this way, you can do the homology, and then if you have some nice facts about the homology, like it doesn't vanish, then maybe you could hope to prove the Weinstein conjecture. That's not really like a good way to try to go about proving the Weinstein conjecture, but it's kind of shows that there's some interesting topology associated to contact manifolds. Okay, so in the 90s, Hofer, Vysotsky, and Zander had many papers about J holomorphic curves in symplectizations. So they showed a lot of really nice properties. They studied moduli spaces of somewhere injective curves, proved that they could be cut out transversely after generic choice of J and given a nice geometric structure. In a symplectization, you do R across the contact manifold. The symplectic form on it is d e to the tau alpha, so here tau is the coordinate on R. And then there's a complex structure that you can put on it. So Cassie J is a almost complex vector bundle, and you can always find, the space of J compatible with d alpha on C is contractible. And because of the splitting of the tangent bundle of M into the context distribution in the Reeb direction, you can find, there's a natural way to extend J to R times M by taking J twiddle equal to J on Cassie, and then J of dd tau is sent to the R direction. And such a J twiddle is called admissible. Okay. And I'll say what a pseudo-holomorphic curve is in just a second. But so in the 90s, Hofer, Vysotsky, and Zander had a lot of nice papers about this, which then led to an infamous paper by Hofer, Hofer by Ellie Ashberg, Hofer, and Giventhal, which was called Intro to Symplectic Field Theory. And so in symplectic topology, we have all these different pseudo-holomorphic curve homology theories, and then based on these results that Hofer, Vazetsky, and Zander had about J-holomorphic curves and symplectizations, Ellie Ashberg, Hofer, and Giventhal basically said, like, if there was no analytic problems, we can, like, sort of generalize this Morse theory pseudo-holomorphic curve approach into something called symplectic field theory, and it would be like the one ring to rule all the J-holomorphic curve homology theories. Okay. But like in the Lord of the Rings, right, this one ring to rule them all turned out to sort of not be such an awesome idea because it brought about a lot of difficulties. So polyfolds will hopefully save us from the shadows of multiply covered curves. Okay, so yeah, that's, I guess, basically the gist. Okay, so let's go back to what this chain complex is supposed to be. So I'm going to write down like it's not a fake action functional, it's an actual action functional. But at some point, the analogy of doing Morse theory on it is going to fail. But kind of just stay with me for a moment. This is there's a secret S1 action floating around. And this action functional is going to be defined by sending a closed loop to its integral around alpha. So we're going to fix a closed, non-degenerate contact manifold M alpha. So you want to fix the contact form on it. And then a pretty straightforward proposition is that gamma is a closed Reeb orbit of R alpha if and only if gamma is actually a critical point of this action functional. Okay, and the reason why there's this secret it's not really so secret, but there is sort of, you need to mod out by an S1 action because you have an S1 action, so there's a S1 action corresponding to the starting point on your closed Reeb orbit gamma. Okay, so sorry. I mean, so when we write down the pseudo-holomorphic curves, there's going to be, you have to consider, so you write down a parametrized pseudo-holomorphic curve, but then you have to look at the space of unparametrized curves. And because of the way that you set up the problem, there's an S1 action on all the Reeb orbits depending on where you pick the starting point, which corresponds to the choice of parametrization. So you have to mod out by this S1 action, which means that the whole theory that you set up has this S1 action acting on it, which is going to be what causes the problems. And also, the other thing is that, so in Hamiltonian Floer homology, you only usually consider time one closed orbits of your Hamiltonian vector field. But in this case, we're going to consider all of the Reeb orbits and all of their iterates in the chain complex, which is going to be what gives rise to the multiply covered curves. Okay. And then there is, so associated to a Reeb orbit is something called the Connelly-Zander index. If you've never seen the Connelly-Zander index before, I'm not really going to have time to define this, but this is a basically a generalized winding number associated to pass the symplectic matrices. And you get this path from gamma by linearizing the flow. Along the Reeb orbit and then restricted to the hyperplane distribution. And it turns out that if h upper 1 of mq equals 0 and c1 of c, this would actually be equal to c1 of r cross m is equal to 0. This guarantees a unique choice of complex volume form on R cross M. So if H1 is not equal to 0, then you'd have many choices of complex volume forms on the symplectization, and this is to sort of take this derivative. And then this will give rise to a Z grading on the chain complex. Okay, so, and it turns out that this is going to be sum of the closed Reeb orbits, which I'll explain in just a second. Okay. And and then I guess, I'll write it on this board so you guys can see it. So this is going to be all non-degenerate closed Reeb orbits less the set of bad Reeb orbits, which I'll explain in just a second. And then the differential is supposed to be a weighted count of solutions up to equivalence of maps. So these are going to be maps from S1 cross R, and you can think of S1 cross R as S2 minus 2 points, and then there's going to be a way to put a complex structure on that, since it's a Riemann surface minus 2 points, into the symplectization with this admissible almost complex structure that I defined over here. And then we also need some asymptotic condition. Oh, okay. So to say that this is a pseudo-holomorphic curve, this means that the d bar equation is equal to 0. So this is that du plus j circ du circ little j is equal to 0. And then we need plus some asymptotic condition. So we'll take gamma plus minus to be Reeb orbits of period t plus minus. Then we need the limit as s goes to plus or minus infinity of a. So a is going to be the component of this map that lives in the R component of the symplectization. we want this to go to plus or minus infinity in the R component of the symplectization. And then when we look at what's happening as we send, so here this is S, sorry, I'm gonna write this as R cross S1. So the S, this S derivative, sorry, this S variable is on R, and the T variable is on S1, and then of H of S dot, we want to be limiting in the M component on the closed Reeb orbit, and we have to include this period factor. And these are both in C infinity, okay, as far as the convergence is concerned. And then there's, so Hofer, Zatsky, and Zander in their series of papers in the 90s had something called a finite energy condition. And it's not really important to know what this energy condition is, but basically the J-holomorphic curves that are finite energy have to limit on these Reeb orbits, and there's a nice like asymptotics that they have, which gives you a nice like function space that you can work with. Okay. And sort of, I guess maybe the first sense that there might be some sort of trouble. Okay, and then obviously, right, if we look at this action functional, these, if we took the gradient of this like, these J-holomorphic cylinders interpolating between closed Reeb orbits aren't going to be gradient flow lines, so that's where the analogy starts to break down. And the equivalence comes from the fact that you have to mod out by this R cross S automorphism group on your domain, and then you're also going to end up having to mod out by the R action on your target. So, so you can write, okay, just write this. So, okay, and then you have to mod out by this R action. And so here's where this like S1 symmetry comes into play, because this Reeb orbit, you only care about its image, you don't really care about its parametrization when you're looking at this count of solutions. And then there's actually two different ways that you can define the differential. So one is to count, so here we have Connelly-Zander index of x minus Connelly-Zander index of y is equal to 1, and this will be the count of all the cylinders in this moduli space m x y, and then you have multiplicity of x divided by the multiplicity of the cylinder, and then either you can do this mod 2 or you need a coherent orientation, which is a sign plus or minus 1. Okay, but that's not really so important, so we're just going to pretend that we can do this mod 2. And then the other way that you can also define a differential is over the same sum. But now we take the multiplicity of the bottom orbit divided by the multiplicity of the connecting cylinder. Okay, and then this bad Reeb orbit condition so there's two ways the Connelly-Zander index of gamma simple can behave for iterates of a simple Reeb orbit. So, okay, sorry. So I'm going to say gamma is a simple orbit. Gamma k is going to be iterates. One is that gamma, the parity of gamma to the 2k is equal to the parity of gamma to the 2k minus 1, or parity of gamma 2k is not equal to the parity of gamma to the 2k minus 1. Okay, so basically what I'm saying is that the Connelly-Zander index can always have the same parity as you increase iteration, or all of the odd multiples are going to have different parity than the even multiples. So then the even multiples are bad if the parity is different from the odd multiples. So then in this chain complex, you would start by having all of the non-degenerate closed Reeb orbits and all of their iterates, and then you're going to throw out all of the Reeb orbits, which are bad, so that'll be all the even multiples of Reeb orbits changing parity. And in dimension 3, you can see this by looking at the eigenvalues of this the linearized flow. And if you have negative real eigenvalues, it turns out that those are going to be examples of give you bad orbits if you consider even multiples of them. Okay. So any questions there? Okay. And then an important thing to notice is that this division, these are that the multiplicity, so what I want to say is that the multiplicity of C actually does divide the multiplicity of X and the multiplicity of Y. Okay, and by multiplicity of X and multiplicity of Y, I mean there's always going to be some underlying simple Reeb orbit for X or Y, and the multiplicity is then the number of iterates you have to take of that simple Reeb orbit. And the multiplicity of the cylinder means that if the cylinder is multiply covered, there's going to be some k-fold covering map of the source that you have to precompose the J-holomorphic curve with, and the multiplicity will then be the degree of that cover. So if you have a J-holomorphic curve that's a two-fold cover of a somewhere injective J-holomorphic curve, then the multiplicity of that curve will be 2. Okay, and the multiplicity of C, so if you have like x squared and y squared, the multiplicity of this curve could be 2 if this is a 2-to-1 cover of a J-holomorphic curve that goes between x and y then. Okay, so you can convince yourself that the only way you can have a multiple cover is if the Reeb orbits are multiply covered, and then it has to be some common factor of the multiplicities of the top and bottom Reeb orbit that the multiplicity of your J-holomorphic curve can be. Okay. So now, the reason why you should be a little bit nervous about what I wrote down for the expression for the differential is because I have this multiplicity of the top divided by multiplicity of the bottom, so that's some sort of weighted count. And in Morse theory or Hamiltonian Floer theory, you don't have a weighted count. You just do an actual count of the solutions or of the gradient flow lines. And so this weighted count means that this moduli space is not going to be a manifold if you've got multiply covered curves floating around. It's going to be some sort of an orbifold, and that's why you have to sort of divide by the multiplicity of the pseudo-holomorphic cylinder connecting Reeb orbits so that you don't end up overcounting. But of course, whenever you have some moduli, so trying to show that some moduli spaces in geometric structure is usually hard. And if you're working with somewhere injective curves, it's usually pretty straightforward, but then you're working with an honest manifold instead of an orbifold. So that's sort of where the trouble is going to come from. So what we want to have is some kind of a theorem that says assume blah, blah, blah. Then C star D plus or minus is a chain complex. And the homology which is dependent on the choice of alpha, because that's where the elements of our chain complex come from, because they're coming from closed Reeb orbits. And the differential counts pseudo-holomorphic curves, which means that we made some choice of J. And at the end of the day, we want to construct an invariant of the contact manifold, which means that we'd want this homology to be independent of alpha. Okay, so the first attempt is to say alpha is non-degenerate. Okay, and this the non-degeneracy condition I didn't explain very well, but basically, if your alpha is degenerate, then it means that all of your closed Reeb orbits are isolated, and you can check whether or not that happens by linearizing the flow of your Reeb orbits, looking at the eigenvalues, and making sure that when you come back after its period, that you don't end up with eigenvalues equal to 1. Okay, so you want alpha to be non-degenerate, so you only have isolated Reeb orbits. J tilde to be chosen generically. And there to be no contractible orbits of index 0, negative 1, or 1. Oh, okay. Sorry, there was one more thing I needed to say. So the grading of gamma is equal to the Connelly-Zander index of gamma minus n plus 3, where the n appears in the dimension of the contact manifold in the form 2n minus 1. So in the purposes of this talk, I'm mostly going to be interested in dimension 3, because that's the only place that I have positive results to say. So in that case, n is equal to 2. Sorry, this is plus n minus 3. So you get CZ of gamma minus 1 is your grading. Okay, so this minus 1, 0, or 1 means that that's the grading on your Reeb orbit. This 0 appears means that the Reeb orbits are contractible. So you want this chain complex to be empty, i.e. no contractible Reeb orbits in C star of index negative 1, 0, or 1. Okay, then you get a homology invariant under the choices. Okay, so this is sort of the dream that appeared in the Eliashberg Giventhal-Hofer paper. But the problem is that we're going to run into some transversality troubles. Okay, so now I'm going to explain why this fails. Okay. So the trouble is that there's no sort of regularity results for moduli spaces of curves which are not somewhere injective. Okay, and I'll explain in just a sec why this is actually a problem. So the dimension, yeah. So the dimension of the moduli space, which is really the virtual dimension if you don't have any regularity results for the moduli space. And you have to consider, so I'm going to explain in just a sec that there's compactness results that mean that we have to consider moduli spaces with not just one negative n, but an arbitrary number of negative n's. This is n minus 3 times 1 minus s. So this will be negative 1 in this talk because we're working in dimension 3. So this is S is the number of negative punctures, plus the Connelly-Zander index of the top, minus the sum of the Connelly-Zander indices at the bottom. And then you also might have to throw in some relative Chern class, but since I assumed that since I assumed that the first Chern class of the contact distribution was 0, I don't have any extra terms in here. And so this means that if M consists of multiply covered curves, we can't assume that the virtual dimension of M is greater than 1, or greater than or equal to 1. Okay, and the reason why this is a problem is because, so in Moore's theory, in order to prove that d squared is 0, you have to look at, so here's x, z. So you have the index of x minus the index of z equals to, and in order to prove that d squared is 0, you need to compactify the space of solutions of index difference 2, and it turns out that a gradient flow line might limit on a once broken trajectory. So here, the index of x minus the index of y is equal to 1. So you might have to include these broken flow lines, and once you compactify this moduli space, you can say that it's a compact one-dimensional thing, so its boundary has an even number of components, and then that's what proves that d squared is 0 in Moore's theory, if you count with z mod over z mod 2. Okay, but in the pseudo-homomorphic curve picture, what happens is you're going to have some cylinder limiting on x and going from x to z, or x to y if you're trying to do invariance. And the trouble is that the cylinder could develop a min. So u in xz, so we can say equivalence, okay, can develop a min in the R component, which I called H, which means that to compactify by the results of Bourgeois, Eli-Ashberg, Hofer, Vysotsky, and Zander, that M bar xz has to include buildings where you have, when you connect everything, that the homotopy type remains a cylinder, but you can sort of cap off everything. You cap off all but one of the negative ends. Okay, and so this does not look like the picture in Moore's theory, where we would need to show that an index difference 2J homomorphic cylinder would have to degenerate into an index difference 1 curve and then another index difference 1 curve. Okay. And the only sort of numerical constraint on, this compactification is that you need that the virtual dimension of all these pieces, or the index of all the curves, has to sum to 2. So here in this, sorry, okay. So here, so that we don't have to worry about keeping track of this -1 all the time. You can either think that the dimension of this piece equals 2, equals 1. Okay, so depending on if you want to keep track of an extra -1 on all these pieces, you can do that. Otherwise, you can think about it in terms of before we mod out by the R action, so this would be 2, and then you would need to make sure that the sum of all the virtual dimensions or indices on these pieces added to 2. So like if this is 0, 0, and 2, then that's going to be something that's allowable in the compactification. And the reason why you can have curves of index 0 is because if you have a multiply covered curve or a branched cover of a curve, you're not going to be able to assume that the virtual dimension of the space is at least 1. Okay. And so you can think about all the different ways that you can add to 2, and you're going to see that if you allow for negative numbers, you're going to have a problem trying to show that d squared is 0. Okay. And then there's an example you can write down with an ellipsoid in 3 dimensions where you can show that you actually will end up with branch covers of a trivial cylinder always having index or dimension 0, and so then you can always show that when you compactify the moduli space, you'd have to include these pairs of pans capped off by a disk with a trivial cylinder, and you'd be in trouble. Okay. Okay. So, any questions so far?
Could you just say the last thing again about the have an example?
Oh, yeah, so an ellipsoid, so with an ellipsoid, E, A, B, so you can write this as where F is equal to norm U squared over A plus norm V squared over B. So this is a 3-dimensional ellipsoid. Then there's this formula for the Connelly-Zander indices, so that's that phi 1 would be A over B, phi 2 is equal to B over A. And then this means that the Connelly-Zander index of gamma I to the k, so if A and B are rationally independent, you take alpha equal to df circ J0, so J0 is the usual complex structure on C. That would be your contact form, and R alpha has 2 simple closed Reeb orbits. One in the U equals 0 plane, and one in the V equals 0 plane. So the one in the U equals 0 plane, we can call this guy should be gamma 2. This guy is gamma 1. And if you're sort of want a picture that's like a little bit dishonest, so this would be like U, or I don't know. Maybe I got my U and my V switched, but this is the ellipsoid drawn in sort of 2 complex variables. Then in the V equals 0 plane, this is going to be a closed Reeb orbit, and then in the V equals 0 plane is this guy, and then the U equals 0 plane is this guy. Okay, and then you can take all of the iterates, and those are also going to be closed Reeb orbits. Okay, and then the formula for the Connelly-Zander index is going to be equal to 2 floor k times 1 plus phi I plus 1. So the grading is equal to 2 k 1 plus phi I. Okay, and so if you pick, either phi 1 is less than 1/2 or phi 2 is less than 1/2. In that case, let's just say that phi 1 is less than 1/2. Otherwise, instead of writing gamma sub 1, I would write gamma sub 2. I get that the Connelly-Zander index of gamma sub 1 would be 2 times 1 plus phi 1, which is going to be a number less than 1/2. So the floor of that's going to be 1 times 2 plus 1 equals 3. And then if I iterate gamma, I'm going to get 2 times the floor of 2 times 1 plus something smaller than 1/2. So I'm going to get 2 times 2 plus 1 equals 5. And then if I consider sort of curves that are a 2 to 1 fold cover of the trivial cylinder, so then let be, so if you let the moduli space consist of these curves, then you're going to end up with the virtual dimension of this moduli space to be equal to, if we look at this formula, the number of negative punctures is 2, so we have -1 times -1, which gives us +1, plus the Connelly-Zander index of the top minus the Connelly-Zander indices of the bottom. So this will be 1 plus 5 minus 2 times 3. And you're not going to be able to exclude this moduli space after generic choice of J because you can't get rid of the trivial cylinder, and so you can't get rid of these branched covers of the trivial cylinder. Okay, and then in the compactification, when you look from gamma 1 squared to gamma 2, so I didn't tell you what gamma 2 was, but gamma 2 is going to be end up being equal to, sorry, what did it do? Oh, no, sorry. Gamma 1 squared to gamma 1, this is index difference 2 because we have 5 to 3. Then this curve, when you compactify, its boundary is going to consist of elements that look like this. So this is gamma, this is gamma. The virtual dimension of this piece is 2, the virtual dimension of this piece is 0, and the virtual dimension of this piece is 0. And so you can see that it adds to 2, which is what you would want. So you'd have to include it in the compactification, and then this is going to make it difficult to try to prove that d squared is 0. Okay. Okay. So the remaining time. So basically, to get around the transversality troubles is that you need to prove A, that all the finite energy cylinders of index 1 and 2 can be regularized, even if they're multiply covered. So another problem that exists in literature is that even sort of if these multiply covered curves don't have negative index, you are not necessarily going to have regularity results. And the only regularity results that exist for multiply covered curves in this setting are due to Wendell. So some positive results due to Wendell in dimension 3. Okay. Then the second thing is that you need to show that there are no cylinders of index less than 0, and the only cylinder of index equal to 0 is the trivial cylinder. And this is going to be in symplectization. So to do invariance, it's going to be a similar story, but a little bit difficult, and I don't have time to get into that, so let's just focus on what's going on with symplectizations. So you can show that this actually forms a chain complex. Okay. And then C, pseudo-holomorphic planes have sufficiently positive dimension. So this kind of goes back to this original sort of assertion in the Folk theorem that there's no contractible orbits of index -101, because if you're able to like sort of cap off pieces of arbitrarily negative index, then you can have positive moduli spaces here and positive moduli spaces there, and you'd have to include them in the compactification. So this is something like, e.g., if gamma contractible, then Connelly-Zander index of gamma is greater than or equal to 3 in dimension 3. And in higher dimensions, instead of having -3, you need to account for that shift with this plus n minus 3 business. Okay, and then finally D, if sort of this moduli, if one of these pairs of pans with an arbitrary number of negative things could appear in the compactification of mxz, then this moduli space is actually empty. So, like, sort of the ultimate dream would be to say there's some perturbation schemes that we can put down so that once we assume that J has been chosen generically and alpha is non-degenerate, then you're going to get rid of all these moduli spaces appearing in the compactification because they'd have negative virtual dimension, which comes from being able to say like the thing is cut out transversely. But sort of, so in my thesis, I didn't like sort of have some magical perturbation scheme. I just figured out that if I impose sort of some stronger conditions on the behavior of the Connelly-Zander index, you can automatically sort of exclude these things from appearing in the compactification because they're empty. Okay. And since I'm running low on time, I'm going to tell you the condition just for sort of if there are only contractible orbits, and explain how you generalize it for non-contractible orbits, but it's kind of a mess of notation to write down, so it's not really so illuminating. Okay, so it turns out that in dimension 3, I proved, so I don't know if you want to count these as theorems or not, that in symplectizations, that A, B, and C are always true for M alpha non-degenerate and alpha dynamically convex. So dynamical convexity goes back to a notion of Hofer-Vazetsky and Zander, which means gamma contractible implies Connelly-Zander index of gamma is greater than or equal to 3. And this is after choosing J generic. Okay, it turns out that D, you have trouble due to branch covers of trivial cylinders. And in dimension, and then this also, so this uses a bunch of different things. It uses some brute force index calculations to show that there are no cylinders of index less than 0 except the trivial cylinder, and regularity results of Wendell, sort of once I have these index calculations in place. Okay, so, and then, that's true. Then, what do I want to say? In a cobordism, or if you pick your almost complex structure on your symplectization to not be invariant into the R action, so if it's not admissible which is what I wrote down as the sort of choice of J, where it intertwines the R direction and the Reeb direction in the symplectization. It turns out that you can't get then you cannot prove B. Well, you can't prove A and B are able to be proven without advanced technology. E.g. polyfolds when they get completed. Okay, and then to get D and A and B in cobordisms, and D will be in symplectizations and cobordisms. You need to further assume that alpha is dynamically so I called them dynamically separated. So you say that alpha is dynamically separated whenever you need, okay, so you also need C1 to be equal to 0 and H upper 1 of M Q to be 0, so that it makes sense to write down the Connelly-Zander indices in this global way. The first condition you need is that if gamma is closed and simple, then the Connelly-Zander index is between 3 and 5, and 2, you need that if gamma k is the k-fold cover of a simple orbit, then the Connelly-Zander index of gamma k plus 1 is the Connelly-Zander index of gamma k plus 4. So the second condition says that every time you go around your Reeb orbit, you add 4 to the Connelly-Zander index. And in sort of the real world, you'll only be able to get that a contact manifold is dynamically separated up to a given action level, and then you can use a filtration and take direct limits to recover the full contact homology. But that's kind of a technical point that I don't have time to get into. And if you have, okay, so this would be if there are non-contractible orbits, then you need to modify it. So every time, so the problem is that if you have so the reason why it's harder to write down is because if you have non-contractible orbits, you might not have a simple orbit in each free homotopy class. You might have to go around that orbit a few times before you get something in the first element of a free homotopy class. And what you need to have happen is each time you iterate within the free homotopy class, you have to go up by 4 each time. But it's like you would write down a list of all of the times you go around the Reeb orbits in a given free homotopy class, and the next iteration that leaves you in that same free homotopy class, you have to go up by 4. And then you need the same bound on contractible orbits, and for non-contractible orbits, you can have it in between any two odd numbers. Okay, so then I think I'm out of time, so I'll end here.